Okay, in this problem, what we want to do is solve this equation, but given that the roots are in geometric progression. So the key here, and we've done this in extension 1, is to let our roots be in this form. Let the middle term be a, and then we have an a on r, and then the last term would be an a times r. So the common ratio, we're multiplying by r each time, but this just makes this very easy to manipulate rather than AR, AR, and AR squared. So it's just always try and remember to do this and let it be this way. Because firstly, you can work out one of the roots. Product of the roots is a on r times a on r. And the r's cancel, so we get a cubed minus 8, and so a would be equal to minus 2. So we're able to start making some inroads straight away, and we've got one root already. So we can then play around with the other one and go, well, the sum of the roots would be minus 2 on r plus minus 2 plus minus 2 on r, because a is now 2. And that leaves us with a quadratic here. And that was equal to 3, obviously. Multiply through by r, we get a quadratic, we can collect all the terms, and we get 2r squared plus 5r plus 2, which we solve to get minus a half and minus 2. So that means our roots would be minus 2 on the r, if I take r to be minus a half, and so that gives us 4. We get a minus 2 and minus a half times minus 2, which gives us 1. So it doesn't really matter whether we take r to be 2 or the half, these will get the same roots. So that's how we work that out. So the key is here to remember where to start. If we can't make that start, then it makes life really difficult for you. So in the next one, we've given the roots form an arithmetic sequence. So when we have this situation, we start with this. We instead of starting with alpha, then alpha plus d and alpha plus 2d, alpha would be in the middle. The one before is alpha minus d, and the one after is alpha plus d. Because again, we're able to say, well, let's sum our roots, and that would just give us 3 alpha, because the minus d and plus d would cancel. And that's minus b on a, so it gives us a positive 3 alpha is equal to 6. Again, gives us one of the roots already. So alpha is equal to 2. Then when we start to manipulate and go, well, let's add them, let's do the sum two at a time, we get this situation. So we can start to say alpha times alpha minus d, the alpha minus d times alpha plus d, and the alpha times alpha plus d. So we get an expansion when we get those. The alpha times d cancel, so we start to able to work that out. We know alpha is equal to 2 because we worked that out before, so alpha squared is 4. So we can do an alpha squared in there, an alpha squared there, as an alpha squared there. We're just left with the minus d squared, which we're able to solve, and we're able to get d is root 3 on 2. So we're able to say d there being root 3 on 2, we subtract, we have the 2 minus root 3 on 2, 2 plus root 3 on 2, and there would be our there's our 3 roots for that. So that's how we can solve that one. So again, if we know the start, it makes life easier, and there's there's how we can write that expression as the sum of the factored form. So in this one, we've got roots of this equation. Now notice it's got a complex constant there, are alpha and beta. So without solving the equation, form a cubic equation whose roots are alpha, beta, and alpha plus beta. So if we're looking at this, we're going to get alpha plus beta is minus 5 on 1, and alpha times beta is minus 2i, because some of the roots and product of the roots of this quadratic. So if we're going to find a cubic that has these roots, so alpha and beta and alpha plus beta, well, again, we can start to expand that out, and we get alpha plus beta, and we know that the sum of the roots here is 5, because we proved it there. So that's where we get the minus of minus 5. So alpha plus beta is minus 5, so it gives us x plus 5 there. So again, what we notice, we've got alpha plus beta there, alpha times beta. We're able to put minus of minus 5 in, so it gives us minus 5x. And alpha times beta was minus 2i, so we're able to put that in. So expand that out, and we can collect our terms in x. And there was our cubic that has roots of alpha, beta, and alpha plus beta. That's how we can work that one out there. And question 8. Alpha plus beta plus roots of that equation. Find the value of alpha cubed plus beta cubed plus gamma cubed. So again, we know from what we've done before that we can get alpha cubed there, because alpha is one of the roots, so we can manipulate this expression, put alpha in, and we can get alpha cubed, beta cubed, and gamma cubed, because they're roots of the equation. We know the sum of the roots 1 at a time is 2, the sum of the roots 2 at a time is 3 on 2, minus 3 on 2, so we can start to put that in. So the sum of the 3 roots gives us those 3 expressions. We collect our terms. Remember when we did the alpha squared plus beta squared plus gamma squared is alpha plus beta plus gamma all squared minus 2 alpha beta, beta gamma, and alpha gamma. So we can make that manipulation for that part. And we've got the sum of the roots, and we just collect our ones there to give us 3. Remember, the half's common, so it stays out the front. So 4 lots of the alpha plus beta plus gamma all squared minus 2 lots of the sum of the roots 2 at a time, 3 lots of the sum of the roots 1 at a time, plus the 3. Get our manipulation all there, put it in the calculator, and we'll get 37 on 2. So as you can see, that technique is a nice one to be able to know as well, and start to be able to manipulate our equations to be able to help us solve these types of equations using the roots and the coefficients of the equations that we're given.